Hi everyone, I am Khalil Ahmed, Assistant Professor of Physics, and the outline of my presentation is angular momentum, torque, relation between angular momentum and torque, law of conservation of angular momentum, and example. Now let us discuss the angular momentum. What exactly the angular momentum? Suppose for an object moving in a straight line, momentum is simply p is equal to mv, that is the mass into velocity. In rotational motion, the analog of linear momentum is angular momentum. It is nothing but it measures an object tendency to spin. In another way, we can define it is the instantaneous angular momentum L of a particle relative to the origin is the cross product of particles' instantaneous position vector and its instantaneous linear momentum. That is, L is equal to r vector cross p vector. The angular momentum is same at every point in an orbit. When it is closer, it increases the speed. The angular momentum of a particle is the same at every point, and the magnitude of angular momentum is given by the equation L is equal to rp sine phi. Here r is the displacement vector, p is the linear momentum, and phi is the angle between r and p, and also the direction of angular momentum which is perpendicular to the plane containing r and p. Here this direction of angular momentum is always perpendicular to the r and p. Now let's talk about the torque. What torque exactly? Is nothing but the moment of a force, or it is the turning effect. The torque is the cross product of position vector and the force, that is tau is equal to r vector cross f vector. Here suppose in the x-axis and y-axis you consider it as the f cos theta, here the theta, and here the f sin theta, r vector cross f vector, which is the torque acting which is perpendicular to this plane. If the theta is exactly 90 degree, then sine 90 degree is 1. So therefore we can define the torque is equal to r cross f vector. The torque acting on the particle is equal to the time rate of change of particle's angular momentum. That is, the tau is equal to dl by dt. When a body rotating about a fixed point, the force on a body is torque, or it is a measure of how much a force acting on an object causes that object to rotate. And also we can define torque is the perpendicular force acting upon the axis from the distance, and the SI unit of torque is Newton meter. Now let's how the angular momentum and the torque is related. Now let us the mass m be the point particle that has a linear momentum p and the displacement vector r. Let the force acting on it to be F. The angular momentum of a particle is given by dl by dt, that is the derivative of angular momentum is equal to derivative of L is nothing but r vector cross p vector, and we can define linear momentum of a particle as m into v. Therefore we can write m into derivative of r vector cross v vector. Using the product rule or derivative of chain rule, we can write this as m into, by using product rule, derivative of r into v plus r into derivative of v. Here this term becomes, by using the cross vector properties, that is the v vector cross v, which is equal to 0. because the angle between these two vectors is 0. If the sign 0 is 0, therefore this term becomes 0. Now we know that from Newton's second law we can define the net force acting on the system is equal to time rate of linear momentum, that is the rate of change of linear momentum. So therefore we can write derivative of angular momentum is equal to m into v vector cross v vector plus r vector cross a vector. So this term becomes 0, therefore it's become m r cross a vector, which is equal to, we know that from Newton's second law F is equal to ma, we can easily write r vector cross F vector, that is the perpendicular force acting on the system. So therefore the net torque is equal to dl by dt. This gives the relationship between angular momentum and torque. Now we talk about the law of conservation of angular momentum. It is similar to the law of conservation of linear momentum, which is the Newton's second law, says that the force F is equal to dp by dt. It is nothing but the analog, that is the tau is equal to dl by dt. The net force, the net external force acting on the system is 0, then linear momentum is equal to constant. In the same way, the net torque, the net external torque acting on the system is 0, the angular momentum of a system remains constant, no matter what change take place within the system. That is, if the system is isolated, which means no external force or no external torque acting on the system, then the total angular momentum of the system is equal to constant. That is, the net angular momentum at initial state is equal to net angular momentum at final state. This is the law of conservation of angular momentum. Know that for an isolated system consisting of n particles, we can write as angular momentum, the total angular momentum is equal to summation of n is equal to 1 to n of L of n is equal to constant. And the examples are spinning volunteer, scatter spinning, diver, cycle motion, solar system, satellite orbiting the earth, etc. Suppose here the angular, if L is this is the rotational axis, this is the moment of inertia. If moment of inertia increases or it decreases, the angular velocity increases. If this decreases, that is the I is equal to mr square. If r decreases, then the angular velocity increases. This is the example of angular momentum. Thank you very much.